what they want you to know, what they want you to know about waves is for periodic motion, just some of the general terms like amplitude, frequency, to be able to like identify those within a wave. And then for sound, you want to know how it's produced, the things like speed and intensity, the Doppler effect. There's a formula for that we'll get into. Also things like resonance. So in terms of waves, there's two types. There's transverse and longitudinal. So light is a transverse wave, whereas sound is a longitudinal wave. And transverse, the direction they're moving, they oscillate perpendicular to that. So if the wave is like moving across, it'll be like up and down. Like if you're moving a rope up and down, the wave's moving across, but the direction that like it's oscillating is different. Whereas for longitudinal, you can think about the slinky in the photo. The oscillations are the same direction as the propagation. So both are moving horizontal. And so like I said, light is a transverse wave, and some of the properties you'd want to know, which is like on the right side there, is that a wavelength is from crest to crest, so like peak to peak, or trough to trough, which is like the low point, so the low point to low point. That would be one wavelength. It's not necessarily from like middle to middle. That will get you half a wavelength. It'd be like middle, skip one, and then down to another. The amplitude is also how far up or how far down the wave goes from the resting position, but only one, not like from the top to the bottom, but resting to either extreme. And so those would be like the main definitions that would be good to know about a wave. For a longitudinal wave, it looks a little different. Amplitude is kind of like how close the coils would be together. A rarefaction is like where they're more spread out. And then wavelength is from kind of, basically, if you were to take one wavelength and keep copying that, you would get the entire wave. It's the same thing with the transverse as well. So from any point to like that equivalent point when you start a new wave pattern, just the amount of chunks that you repeat basically. But you probably won't be asked to identify those in longitudinal waves because it's a little harder. So as long as you get them in transverse, you should be good. And then, the opposite of a rarefaction is a compression. So those are like two terms for longitudinal waves: compression when they're close together, rarefactions when they're spread apart. So you might want to know about the motion of sound in different states of matter. So sound needs a medium to move across, which light doesn't. And so the velocity of sound will increase with temperature. So it'll move faster when it's hotter. And it also increases if your phase of matter is denser. So it's the slowest in gases, but it gets faster in liquids and then even faster in solids. And so solid would be the fastest there. And you can kind of see in the photo, there's like the sound wave and then the reflected wave. And if it's changing material or changing phases of matter, there might be attenuation, as you can see. So the wave will get less intense because some of it is being reflected. So you can see like the black line and the gas is getting kind of more gray in the liquid, which is trying to show that it's getting a little less intense because some of that is actually just getting reflected at the boundary. So those are just things to know about sound. So quick question here about what we just discussed. Feel free to put it in the chat, either to everyone or just to me. Okay, so I've gotten some direct responses. So it's going to be C, like some of you said, and as we said, so sound moves fastest in solids, and that's again because of the intermolecular bonds, and like the molecules are closer together in solids, so it's easier for the wave to propagate through it. And also, these temperatures are pretty close, but like we said, as temperature increases, It gets faster, so there's two ways you could answer this. If you looked at the state of matter, iron would win, but then also even if you look at the temperature, it's also higher temperature. So both agree, and that would make it the fastest. Another question? Okay, great. Got some responses. And yep, it is C. And so we already kind of discussed it moving in solid, liquids, and gases. The thing about sound waves is it needs matter to move through, like it moves through molecules. And so there has to be a medium. So any state would work, but vacuum is where there is no molecules, like it's just devoid. And light can move through a vacuum, but sound cannot. So that's just like between C and D, that would be maybe the one thing. So it's important to know that like sound needs a medium, light does not necessarily need a medium. All right, and then when we're measuring sound intensity, the units we often use are decibels, but the decibel scale is a logarithmic scale, so it's a little interesting and worth going over. So if you have, say, 0 decibels, that's like your baseline relative intensity times 1. But for every like 10 decibels you add, you're actually multiplying the intensity by 10. So at 10 decibels, your intensity is 10 times more. And you can see this from the formula that's actually used to calculate decibels. So sound level, the beta being like the sound level in decibels, is 10 times the logarithm of the intensity of your sound divided by I naught, which is just like the threshold of received hearing. So like the quietest thing you could hear is 1 times 10 to the negative 12 watts per meter squared. We'll get into that unit in another slide, but that's like the lowest thing you can hear. So it's like the intensity of what you're hearing divided by the baseline. Take the logarithm and multiply by 10. So it's important to know that it's not going to be like 10, like 20 decibels isn't double 10 decibels. It's actually 10 times it. So every 10 you add in decibels, you're actually multiplying the intensity by 10. So worth noting there. And then if you want to calculate a change in sound level, and maybe you don't need to use I naught, then you can use the formula at the bottom where your final sound level is going to be the initial plus 10 times the log of the ratio between the final and initial. But at least I'd say the first formula is more important, and also just having a general sense of like decibels not being addition of intensity, it's multiplication. And so as we saw, the decibel or the intensity unit was in watts per meter squared. And this is kind of how intensity and distance work. They have a inverse squared relationship. So as you see there, I is proportional to 1 over r squared. So as your distance increases, your intensity is going to decrease at a squared amount of that. So if you, as they say, take like half, or if you double the distance, if you go from r to 2r, your intensity is going to be a quarter. So that's also good to note that it's a squared relationship there. You can also see it in the graph that it's like a curve and not just a line going down. So another important relationship to note. And that's also why it's like watts per meter squared. The meter squared in the denominator can also clue you into this relationship. Another thing to know about sound is the Doppler effect. You might have seen it in your practice questions and stuff. So the Doppler effect is that your observed frequency will change if something's moving. So if you're hearing like an ambulance siren, if it's moving towards you or moving away from you, it might sound different since it's moving. So on the left, there's like a stationary source, and that's just the frequency you're hearing it at. But when it's moving between two people, the lady in pink that's moving away from is going to observe a decreased frequency. whereas the man in green that it's going towards is going to observe an increased frequency from the baseline. And then there is an equation for that, which is good to know. It's a little confusing, but basically there's like a plus minus at the top and then a minus plus at the bottom. So you're either going to do plus on the top and then minus on the bottom, or minus at the top, plus on the bottom. So they're going to be opposite signs based on if the object is moving away or towards. So good to be familiar with that. And so V is just like the wave velocity, and then you add on the observer's velocity and the source velocity. So the source of the sound, and then if the observer themselves, so if the people in that photo were moving, you would also factor that in. Then you take that whole ratio and you multiply it with the actual frequency to get the frequency you'd be observing. So one way to remember also, if it's like, if you're doing the plus minus or the minus plus, is to also just like know the general principle of if it's moving away from you, the frequency will decrease. And so that means you'd want that fraction should be something less than 1. And then if it's moving towards you, it will increase. So that fraction should be more than 1 is also worth if you're tripping up over the signs. Okay, and so next thing we move into is standing waves. So they look kind of like this, where you have like a fixed wave, like the ends are fixed and it's just oscillating. A node is where it's like fixed at the resting position, or if in the middle, it's also staying at the resting position. So for like wave A, it's just fixed and there's no nodes in the middle, but there's the 2 on the ends. Whereas for wave B, there's also a node in the middle. You kind of have like a full wave pattern going on. And so you have one wavelength, like the length of that string is one wavelength, because you're going from like resting position, skip 1 to another resting position. Whereas for the first one, the length of your string is just half a wavelength, because if you have just this, you would need another down to get like the entire wavelength. And then antinode is the opposite of a node. So antinode, where it's labeled with the green A in the photo, is like where it's the highest or lowest point there. So these are called also harmonics. So harmonic, the number would be the amount of half wavelength. So we have like the first harmonic, second and third in this photo. And then just to remember node, like no displacement, kind of sounds like node. So that might be one way to remember it. And then you also can get resonance in pipes, and it's open versus closed pipes. So pipes could be open on both ends or closed on one end, open on the other. And so it's good to know that where it's open, it's going to be an antinode, and where it's closed is going to be a node. And the vowels match versus the consonants also match. So on the image on the left, it's open on both ends, and so you have antinodes on both ends. Is that like a high or a low on both of those? And then whereas on the right, the closed end, it's at a node, so it's at like the middle resting position, but then on the open side, it's at an antinode. So it's good to know that. And so then you can also see the first, second, and third harmonics on the open pipe. Whereas for the closed one, you're looking at the first, third, and fifth, because the harmonic is given by the amount of quarter wavelengths. But for an open pipe, it's given by the amount of half wavelengths. Just kind of like terminology, it's good to familiarize yourself with. You can also just think about how many ways can I actually make this happen. Like the simplest way you can make it happen will be your first harmonic. So if we go back, like the simplest way to go between 2 closed ends is just loop over. And then for here, the simplest way to go from an antinode to another antinode is to just go down, or just go like from up to down or down to up. And then the next way would be like up to down to up again. That's like your second. For the closed pipe also, the simplest way to go from the middle to an antinode, like a node to an antinode, is to just go up or down. So you can kind of think of it that way as well if the fractions are harder. The first harmonic is always just the easiest way to fulfill those conditions. Okay. question about waves. So the first harmonic is also sometimes called like the fundamental wavelength. Fundamental is like just the baseline. All right, got some responses. So it's going to be 2 meters for an open pipe. So it's open at both ends. So the diameter, first of all, it doesn't matter. You're looking at like the length. And both ends are going to have their maximum amplitudes. And so for the, it's going to be antinodes on both ends. And so if your pipe is 1 meter long, 2 meters is going to be your whole wavelength. All right. So another thing that was like in the AAMC was ultrasound. It was like in their list of things for sound waves. So something to note about ultrasounds, it uses very high frequency sound waves that are like outside your hearing range, so you can't hear when they do an ultrasound, but you can use it to compare relative densities of tissues. And so it kind of generates the wave and then it reflects off of the objects and returns it. And so the transmitter is also the receiver. So it's sending out the wave and then also getting it back. And then from there, it can look at the densities of tissues to generate, say, images or things like that. And then so we move on to light and optics. There's actually a lot of topics they want you to know for light. We'll go through these. It's like mirrors and reflection lenses, which I believe last week people were also saying they wanted to learn about. So I have some graphics for those. Also just like the general properties of light. So light is an electromagnetic wave, which we can see the entire electromagnetic spectrum on the left there. And so it ranges from long radio waves all the way to gamma rays. Visible light is actually kind of a small amount in the middle of the spectrum, but there's a lot of other forms as well. And in terms of the visible, I would say know that it ranges from like 750 to 400, that like red is the longer wavelengths and then purple is the shorter, just like benchmark where they are. It did end up coming up in my MCAT. It was like a carrot would be at what wavelength, and so you had to know that orange was around 600 or something like that, or like 650. But just like have a general idea of where visible light ranges in the spectrum. And then in terms of just what an electromagnetic wave is, they look like the photo on the right there, where they have both E, like the electric field, and the magnetic field B, and then they're both perpendicular to the actual direction of motion. So in this graphic here, the wave is moving in the X direction, and then the electric waves are like the electric field is in the Y direction and magnetic in the Z direction. So all three of those kind of are the 3 dimensions. And then it's also important to note that these waves all move at the speed 3 times 10 to the 8 meters. That's like the speed of light. C is the constant for that. And so for all of these different types of waves, like the speed of light is 3 times 10 to the 8 meters per second. It's a good constant to know. Oh, okay, I guess I already kind of went into this, but visible light was like that section in the middle. And it's good to know like the benchmarks of where every color is, or you can just know like if it's 400 to 750, where Roy GBIF stands on that. And again, red is the higher wavelength, 750. Purple is the shorter wavelength. And wavelength and frequency are inversed. So that's part of this equation here. Velocity is frequency times wavelength, the lambda being wavelength, f for frequency. This is also important to note that like velocity is fixed based on other things, and then frequency and wavelength will change to adjust. So for light, for example, all of those I said go at the speed of 3 times 10 to the 8 meters per second. So if something's higher frequency, it's going to be lower wavelength, or if it's vice versa, either way, f times lambda will equal that speed. So that's why like frequency and wavelength are have an inverse relationship with each other. One goes up, the other goes down. Another thing to know is the index of refraction of an object. So C, that constant, is like the speed of light in a vacuum. So when there's no molecules, no medium, that's how fast it goes. But it'll be slower when it's actually moving in something. So when it's like, even in air, it's like slightly slower, or like versus like in water and stuff, it's going to move a bit slower. And so to get like the index of a material, you would take the speed in a vacuum, so the 3 times 10 to the 8, and then divide it by what that speed is in that actual medium. So like in glass or something like that. I think for water, the index is like 1.33. So it would be that divided by the speed of light when it's in water. And so it's always going to be faster in the vacuum. And so the index is always going to be above 1. Like air is like 1.003. So it's like barely different from moving in a vacuum. But yeah, the higher it gets, then the slower the speed of light is in that medium. And you're going to need that index of refraction for Snell's law later on. But we also have this question. If you guys got it. So it's going to be D. So as we mentioned, sound speeds up in like liquids compared to gas and solids compared to liquids. So sound is going to speed up because it's moving from a gas to a solid, but light will slow down because it's moving to a denser material, and the index of refraction is higher for glass than it is air. So for light, it's slower in denser materials, but the sound is actually faster. So good. And you guys remembered from before, which is great. Okay, another question. And then remember the formula V equals F lambda. Okay, so I had some mixed responses sent to me. I'll clarify. So one thing to know about like frequency, the unit it's usually in is in hertz, which is like the inverse of seconds. So it's like 1/seconds. So here when it says the waves strike the shore every 3 seconds, that's one wave, sorry about the writing, per 3 seconds. So your frequency is going to be the inverse. So you have one wave every 3 seconds. So in 1 second, you're going to get 3 waves, if that makes sense. And so that would be important to convert for finding this. So it ends up being 0.67 there. Oh, wait, let me clear the drawings. Okay, there we go. And the wavelength also, it's saying between, I guess the wording's a little weird, but adjacent crest and troughs is 1 meter. So the wavelength is twice that because you want like a crest to crest to get your wavelength or a trough to trough. And now it's just saying a crest to a trough, if that makes sense. So all of that, so the 1/3 frequency times the 2 meter wavelength will get you to the velocity of 2/3. Another thing about light is diffraction. So there's like the wave particle theory of light, where light can be either a wave or a particle like photons that we'll get into later. But diffraction is one of the proofs for the wave theory of light because it splits into a wave if you pass it through slits. There's a lot of different types with different formulas. The 3 here, so there's single slit diffraction on the left. And so you pass your wavelength through just one slit, your light through one slit, and then off of the angle that it makes, you can calculate that based on the width of your slit and wavelength of the light. So that's the formula there. And then m being like an integer, like 1, 2, 3, to see which part of the wave. So like the 1 would be like the max, and then you'd get like 2, 3 if you're trying to get further off because that angle is going to increase as you go. And then something similar for double slits. If you pass it through 2 slits, you take the distance between the slits rather than like the width of a slit for single slit diffraction. And then lastly, there's graded diffraction where there's just a bunch of slits. And again, you'd need the distance between. So as long as there's multiple slits, you want to take the distance between them. But graded diffraction will also kind of split up light to the point, like if you're putting in white light with all the colors, you can split it up into the rainbow, which is why people might use graded. But single and double are more common for just like one type of light. So that's all proof for theory of light. And so since you're seeing this wave pattern and like the different intensity bands that you can see, it proves that light is a wave because it splits up that way. And then the index of refraction we were talking about earlier comes into play with refraction and Snell's law. So if we recall, the index is c/v, so the speed of light in a vacuum divided by the speed in the medium you're talking about. And so for Snell's law, if you have light moving from one medium to another, it'll refract, so the angle changes a bit. And you can solve for that with this equation. So you can see on the left, basically, it's going from water to air. So you take the angle with the transverse. So not the angle to the boundary, but the angle to like 90 degrees from the boundary, theta 1 there. That's your angle of your incident ray. And then you have like the n of water, like 1.33. And then you'd use the n of air as well to get that angle theta 2 that it would refract at. So if it's going to something less dense, it'll refract away. So as you can see here, like the angle got bigger, but if it was moving the other way around from air to water, it would get closer to that dotted line. There's also an angle called the critical angle, and that's basically when the angle of refraction is going to be 90 degrees. So if theta 2 is equal to 90 degrees, it's going to kind of move across the boundary. That's critical angle. And then anything greater than that, it'll just reflect. So on the right side, like that angle is greater than the critical angle, so it's not going to refract into the air. It'll just reflect within the water. And the critical angle to solve for it, that means you know your theta 2 is going to be 90 degrees. So sine of 90 is 1. So basically to find the critical angle, you just know that the sine of that angle is n2 divided by n1. So into Snell's law, you know your theta 2 is 90, so that whole sine term is 1. And so you can just divide out the indices to solve for your critical angle. Here's another question. Okay, so I got some responses. Basically, what this one's getting at is like your fiber's made of glass and the light's moving within it, and it's not escaping into the nearby air. So like it's staying within the fiber itself. So to do that, it's the property of reflection because it's going through total internal reflection, which was like the right side here. So it's going at that angle where it can stay within the glass instead of escaping to the air or whatever is nearby. And so that's what they mean by like loss of amplitude, would be like losing some of it to the environment. So total internal reflection is basically what they're hinting at there. So moving on to mirrors, the simplest are just plain mirrors. They're straight, and the angle of incidence will equal the angle of reflection. So pretty straightforward there. Your theta and your theta prime are going to be equal in the image there. It's also good to know that you're going to have a virtual image, so behind the screen, and it's going to be the same distance as the object is from the screen. So you can see like the O and the I are equally distant from the plane mirror, and the reflection is just incident equals reflected. Here's a quick question about plane mirrors. Okay, yeah, so for this one, as we mentioned, the object and the image are equally distant away. So if they can't see 300 centimeters, like they can only see up to 300 centimeters away, you want to be 150 from the meter, so the mirror. So you to the mirror will be 150, and then the mirror to the image is another 150, which gets you to the 300 maximum that you can see. And then we get into the tougher mirrors, which are the spherical ones. So there's a lot of properties to know about curved mirrors, one of which is the focal length. And the focal length is half of the radius of curvature. So it's like curved to be kind of like a section of a sphere. So if you were to take what the radius of that sphere would be, half of that is the focal length, as you can see. So the R would be like the black dot there is like the center. If that were the entire sphere, focal length is half that distance. For mirrors, it's just practicing the drawings kind of helps get the hang of it. This is just like a shortcut in terms of convention and in the equations. So things like if there's an O in the equations we'll get to later, it means the object's in front of the mirror if it's positive, and then negative would be if it's behind, but like your object will always usually be in front of the mirror, whereas your image could be both ways. So the image, a positive image would be a real one that's in front of the mirror, but for example, like plane mirrors we were talking about, a lot of images are virtual and behind the mirror, and that would be a negative to the number associated with the distance of the image. So things like that. For concave versus convex mirrors, there's also a sign convention. And then if your image is upright, that would be positive, inverted is negative. So these are ray diagrams, which is one of the more helpful ways of like figuring out mirror questions. So one type of mirror is concave, also known as converging. And so it's one we see here. And basically the result will depend on where you place your object in relation to the focal length, as we can see. So in A, object is placed beyond the focal length. And so we have that it's a real image because it's on the same side as the object there in front of the mirror. It's also inverted. If the object is placed at the focal length, there will be no image. As you can see, all the lines are parallel, and so there's no image constructed. And then if the object is between the focal length and the mirror, you'll get a virtual image that's upright. As you can see, it's on the other side of the mirror. And in terms of ray diagrams and actually drawing them, the minimum you want to draw is a ray that's parallel to the axis and then reflects through the focal point. So that's like the green line in all of these. So it starts off straight, and then when you're connecting it, you draw it through the focal line. And then you can also do one the other way around. The red line in these is going to be through the focal point and then reflected back. The only exception is in the middle one. Since you're standing at the focal point, you can just do it like reflecting across, but it's also just good to know if the object is at the focal point, you'll have no image. And then for C there, you can also see if the rays are, if they're parallel like in B, there'll be no image, but if they're like diverging, that means you actually have to draw the image on the other side. So you'll have to like retrace the dashed lines back to get where the image would be. So then where they intersect, as you can see in A and C, where those two lines intersect is where your image will be. There's that. And then the other option is diverging mirrors. There's no really cases for this because it's going to be a similar situation where you have your object and then your focal length. So as we saw in the slide before, yeah, so your F, as it says here, F is negative in diverging mirrors. So your focal length, you're going to put it behind, and then you just have your rays. Same principle on actually drawing the rays, where one's straight, the other one passes through the focal length, and then one passes through the focal length, or tries to at least, and it bounces off the mirror and goes straight. And then especially for diverging, you're going to need a lot of dashed lines, as you can see here. So the dashes of the red, so just for the red line in the diverging, the first one, like the diagonal dash line, is just to show that they drew that first line connecting to the focal point, but you're going to base your image off of the second one, the straight one. So for both times, you want to base your image off of the second line you drew. So that's for mirrors. The next thing would be lenses. And so they also have sign convention here, where if you're on the same side of the lens as the light source, and then your image could be real or virtual, so that side or the other. And then it's also important to note that convex is diverging for mirrors, but converging for lenses. This stuff is just like things I would say to memorize because there's not really mnemonics or a great way to know it. But concave is converging for mirrors, convex is diverging for mirrors. But now we get convex is converging for lenses, and then concave is diverging. And you can't even match up the cons. So important to note that it switches between mirrors and lenses. And then, yeah, so just to note the positive and negative when you're drawing it out. Two equations to know. Sometimes you won't have to do a drawing if it's just like they give you the numbers to do the math. One is that the thin lens equation, so 1 divided by your focal length, is equal to 1 over the distance to your object plus 1 over the distance to your image. Again, beware of the sign convention. So like your object will pretty much almost always be positive, but your image, positive if it's on the same side if it's real, but if it's on the other side of the lens, you'll want to use a negative. And then also important to note that, as we said, the focal length is half of the radius. So the 1 over f is also equal to 2 over r. And then another equation is the magnification equation on the bottom left there. And that's that your magnification is pi over ho, and that's also equal to negative di over dou, you could say. So it's the height of the image over the height of the object, and it's equal to negative distance of image divided by distance of object. The reason you kind of need the negative there is because your image will usually be, if your image is one's positive, one's negative, then the height will also be flipped. So then pay attention to the negative sign there. But that height can be negative if it's upside down. So pay attention to the sign convention, and then the magnification. So you could either calculate the magnification or be given the magnification, then have to calculate like the height of the object or like the distance of the image, or you could not need the m, but just use the other 4 things there that based on like the relationship between the distance, what is the relationship between the height. So here is a practice question for that. Okay, I'm getting some different answers here so we can work it out. So it's asking for ratio of height to height of image to, oh, whoops. I thought I turned on annotation, but anyways, yes, so it is 1/3. Let me try to draw it. Oh, there we go. So it's asking for the pi over rho, so we know it's going to be negative di over dou, and the f will end up canceling out because we have both of them in terms of f. So your distance of the image is 4/3 f, and it's also on the other side, so this is gonna be your negative 4/3, and then your distance of the object is gonna be a positive 4f. So the negative from the image cancels out with the negative in the equation. So you're basically gonna have it's like 4/3 divided by 4. And so from there you'll get 1/3 as the ratio as shown here. We also clear the drawings. So it's going to be 1/3 based on. So that's the magnification equation. Here are some ray diagrams for the lenses. So you have the convex and concave lenses. You want to draw, so if you're looking at a converging lens, the name there is kind of helpful. So for a converging lens, you can draw them all parallel and then they all converge at the focal point, or which would be in A, you can see there. Or if you're looking from the focal point on the other side, it will be spreading out and then going parallel. And then for diverging lenses, they'll usually have virtual images since the rays actually get diverged and you have to like dot the lines back. So on the right side, you can see here, converges to the focal point, or it goes and it diverges, and then you have to like draw the dotted lines back. So this is like a summary of all the different lenses and also the definitions. So for a converging system, converging for a mirror would be concave, but for a lens would be convex. And then diverging for a mirror would be convex, but for a lens be concave. So that's why I drew those in. And relative to your object, that's also what the mirror would look like, as well as the lens shapes. So this is just like a good reference. You can also know what the image is going to be if you want to just like not like avoid the diagrams and just memorize this. You can know what the image is going to be based on how far your object is if it's a converging system. For a diverging system, it'll always be a virtual upright, and then reduced being like the size, the height will be smaller. And then for converging, it depends on where the object is relative to the focal point. So like we said, for example, O equals F means no image. An application of lenses is eyes and eyesight. So myopia is nearsightedness and hyperopia is farsightedness, and you can fix that with lenses. So first of all, what the thing actually is. So nearsightedness, your image is focusing in front of the retina, whereas for hyperopia, farsightedness, it actually focuses behind, and then you can use a lens to correct that. So for nearsightedness, you would use a diverging lens. So you can think about like if it focuses too soon, you want to diverge them a little bit to get further and actually focus at the retina. And then for hyperopia, you want a converging lens because it's converging too far, so you want the lens to converge it sooner, if you will. And so those two different types of lenses work for two different types of eyesight conditions. So here's a question about that. Okay, so in the interest of time, I'm going to keep going. So yeah, like we said, it's going to be in front of the retina for nearsighted, also known as myopia. And so you're going to need a diverging lens to diverge it just a bit further. Let me see how many slides I have left. Okay, not too bad. Okay, we'll go a little faster on these to get in the time. There's only one group of subjects left, which is just atomic nuclei, sort of. And some of this, as you can see, is shared with Gen Chem as well, but I thought to put it in here. So one thing they ask about is decay. There's different types like alpha, beta negative, positive, gamma, and electron capture. So these are the general formulas to know. So the general formula of nuclear decay is at the top there, and it's that you'll have your atomic number A and your mass number Z of your species, like X. So that could be like carbon, beryllium, like any atom. And then you also do have access to the periodic table. And then it'll change to a new atomic number or new mass number, and then also emit a particle. Your X and Y could be the same thing if your A stays the same, if that makes sense. If you have the same amount of protons, that's like inherent to what your atom is. So if you have, say, like hydrogen, that's going to be hydrogen as long as it keeps the same amount of protons. But if protons change, it could be something else. So these are just the general formulas that are good to know. So for example, for alpha decay, what happens is you'll have your initial particle, and it'll emit an alpha particle, which is basically a helium. Nuclei has, oh, I switched them, didn't I? Sorry, the atomic numbers in the bottom, mass number at the top, but it's gonna have 2 protons and then a total mass number of 4. So it also has 2 neutrons to get the total number to 4. And then, so whatever you end up with is gonna be kind of 2 to the left of it in the periodic table. So you lost 2 protons and you're gonna end up with a different atom. And then it's also gonna have a mass that's 4 lighter. So protons and neutrons contribute to the mass, electrons don't really. And so these are all the different types of decay. So it'd be good to just know the formulas. There's also photos here with examples. Okay, so for example, in the top left, you're creating uranium because you're losing those 2 protons to the alpha particle. For beta decay, a neutron becomes a proton and an electron for the beta negative. And so you'll actually go like 1 to the right on the periodic table, for example. And then the reverse of that is electron capture, where a proton and electron become a neutron. And then for gamma emission, you don't actually change what the atom is. It'll stay whatever it was before. In the interest of time, I'll skip the question and then talk about half-life. So half-life, this is the formula for it, where basically you want to see like how many half-lives are passed to see what the new quantity of the material is. Usually it's like something's decaying in, say, mass, for example. You would use the old mass and multiply it by half raised to the power of how many half-lives have passed. So the time elapsed divided by the time for a half-life. So if a half-life is 1 month and 3 months have passed, you would do 3 divided by 1 to get that 3 half-lives have passed. And then that's just how many times you have to multiply by half, basically, and then multiply by that initial to get how much is remaining. You can also see it's like exponential decay, so the graph will look like that. Another thing they want you to know is the photoelectric effect. So it's basically that if there's a certain amount of work put in based on the energy of light, there will or won't be kinetic energy to your particle. So the work function, the W there, is kind of considered the potential energy of your electron. And so if the energy of light is less than the potential energy, then nothing's going to happen, as shown on the left there. But if your energy of your light is higher than your potential energy, then you'll also have some kinetic energy. So if HF is greater than W, then you have that half mv squared is going to be greater than 0, and you're going to have a low velocity. Or if HF is way higher, you'll have a high velocity. So by shining light, you can get electrons. So this is part of like the particle theory of light, whereas shining certain lights can emit electrons from a metal plate. Yeah, I think all we have left is questions. Okay, yeah. So this will be uploaded if you want to go back to the questions. But I also have to head to the next Zoom, which is the Q&A one, like the group study one. So if you have any more questions about this, feel free to hop, but I think it is another Zoom, so we can go there. If there's any quick questions, you can drop them in the chat right now. Otherwise, I'll see you guys in the other Zoom. Thanks for coming.